yesterday we talked about these trigonometric functions and angles. So I said that there is, one of the special triangles we have is the 45-45. And the 45-45, the adjacent and the adjacent and the opposite are the same length, because basically it's a nice isosceles triangle. And then we also talked about a 30-60, right? And so if you have a 60-degree angle, then the ratios are 1, 2, root 3. And so those have certain trigonometric values. Now these are the decimal approximations. But what I can do is I can draw a circle, all right? And there's two types of circles. This one's called the unit circle. And I can draw these triangles such that this is a measurement of theta, right? And this is the opposite, and this is the adjacent, and this is the hypotenuse, which is also the radius of the circle. Now the unit circle, the radius is 1, but we can have a radius any size, all right? And so remember that your trig functions, these values correspond to the ratios. In other words, do you guys remember what sine is? What two sides sine represents?
So opposite over hypotenuse.
Opposite over hypotenuse. And so what we need to find is the correlation, or what we're going to talk about today, is the correlation between drawing these triangles within a circle, the x and y values, and what they represent in the unit circle, and how that graphs the ratios. So right now, this is a great visual tool. I'm going to start here. I want to explain some things to you. When we measure in trigonometry, we start on the positive x-axis, and we rotate counterclockwise around. And notice as I rotate around, I can draw, well, basically 4 different types of triangles. Also notice that the triangles always go back to the x-axis. Does that make sense? Now, in the past, you guys have graphed the trig functions. And the trig functions, what does the sine wave look like? Make the hand motion. Yeah, it's like a wave. That's why we call it a sine wave, or the sine function. Now, where this comes from is, if remember that sine represents the ratio of the opposite over the hypotenuse, as theta changes, okay? And I'm going to pause right here. Right here, our measurement for theta, our angle is 32.2 degrees. Now at 32.2 degrees, the ratio of the opposite, this right here, over the hypotenuse right here is 0.533. So as I rotate around this circle, my value for sine will change. And the reason it changes is because the ratio is of the opposite over the hypotenuse. And so as my triangle changes, so does that ratio. All right? Now, here's the interesting thing. That ratio reaches its peak when I've moved 90 degrees. At 90 degrees, on the unit circle, the sine function value is a positive 1. So this is, if I put the function sine of x in my calculator, I would get a graph that looks like this. Where that value comes from is drawing this triangle within a unit circle, or a circle that has a radius of 1. As I rotate around, notice that my values change, but what do you notice about the opposite? Well, the opposite is actually the y value, right? And think about that. If the opposite is the y value of the coordinate point, and it's over the hypotenuse, which is the radius, which is 1, what's 7.08 divided by 1? 7.08. So as I rotate around through this function, notice that my sine value changes. Now, when my y value becomes a negative y value based on its location on the xy plane, look at what happens to the graph of the sine function. It becomes negative. Now, the reason for that is that here, my y value of this point is negative 0.798. The hypotenuse is still 1 because it's the radius of the circle. So negative 7.98 is divided by 1, which gives me negative 0.798. So when we get down here at 3 pi over 2, or 270 degrees, we reach the minimum value for the trigonometric function. Now we call these circular functions for the obvious reason. These values are based on going around the circle, but what happens is as you continue to go around the circle, the pattern repeats. So if you continue to graph the sine function, what happens is you get this wave function that extends beyond what we could see on the screen. Does that make sense? Now, I'm going to turn sine off. Cosine is the adjacent. And so you get a similar pattern, but if you notice, the adjacent is actually the x-coordinate of this coordinate on the circle, right? And since the hypotenuse is equal to 1, because cosine is the adjacent over the hypotenuse, I really get the 0.84 divided by 1. So cosine of 32.9 degrees is 0.84. And so we get the same phenomenon here, but the graph just looks a little different. All right, so now I'm going to turn them both on. You see that we have what we call sinusogenous behavior, and that's just a fancy word that means that there's a wave that repeats itself. Okay? Now tangent, believe it or not, is the opposite over the hypotenuse, which is really sine divided by cosine. And so if I turn tangent on, whoa, we get some crazy stuff. But let's start here. Tangent has a different value because what it's comparing is the opposite, which we know to be the y value, divided by the adjacent, which we know to be the x value. So tangent is really the y divided by the x. Does that make sense? All right. So the graph looks a little different. An interesting thing is that when cosine is equal to 0, what does that do to tangent? Well, because cosine is in the denominator of tangent, you're going to get a vertical asymptote when cosine equals 0. So cosine actually equals 0 at 90 degrees. What is the value of tangent? Well, there's a vertical asymptote. Right? Because we can't have 0 in the denominator. So basically, these are what all three graphs look like, and this is what they're based on. It's rotating through the unit circle. Okay?